By 2032, India's industrial sector is projected to hit peak capacity, requiring a massive surge in reliable power generation to sustain its growth. This chart shows India's projected 2032 energy demand. Required output far exceeds the fossil fuel baseline, but net zero commitments prevent coal from closing the gap. While solar and wind expand, their outputs fluctuate, unable to provide the continuous baseload required. Nuclear energy remains the only scalable, zero-carbon technology capable of providing this industrial baseload. However, this map reveals a domestic resource constraint. India lacks significant uranium reserves, creating a dependency on foreign imports. Conversely, India possesses a massive geographic advantage along its coastlines, holding some of the world's largest thorium reserves in monazite sands. To achieve true energy and economic independence, India must engineer a physical pathway to convert its domestic thorium into usable fuel. Decades ago, Dr. Homi Jehangir Bhabha designed a specialized reactor sequence specifically to solve this thorium-uranium paradox. This flowchart illustrates the three-stage nuclear program. It is a closed-loop system where the radioactive byproduct of one stage is intentionally harvested and refined to serve as the fuel for the next. Executing this vision is a multi-decade structural trend, requiring a massive scale of national infrastructure. The financial expansion of this sector is concentrated in the private proxy companies contracted to handle the heavy engineering and component manufacturing for these plants. This network requires immense capacity in heavy engineering, precise EPC operations, and advanced metallurgy. The specific physics of this three-stage loop dictate the long-term order books for these heavy infrastructure and engineering stocks. This 3D cross-section shows a pressurized heavy water reactor forming stage 1. Inside, natural uranium undergoes fission. This generates heat, converting water to steam to spin turbines for baseload power. During this, uranium-238 absorbs neutrons, transforming into plutonium-239 for the next phase. Housing these reactions safely requires massive, airtight civil containment structures, often built with specialized high-strength concrete. This architectural wireframe highlights the scale of the required civil engineering. Constructing these domes requires core EPC players like Larsen & Toubro, Bharat Heavy Electricals Limited, and Hindustan Construction Company. Stage 1 provides immediate electricity while creating a long-term revenue pipeline for India's heavy civil construction sector. Stage 2 shifts to fast breeder reactors, which utilize the plutonium-239 harvested from the first stage. This diagram shows the breeder mechanism. Plutonium undergoes fission, and high-energy neutrons strike a surrounding uranium-238 blanket, transforming it into more plutonium. Because it generates more fuel than it consumes, Stage 2 exponentially increases India's fuel availability. Managing these high-energy neutrons, along with advanced liquid metal coolants, requires complex mechanical manufacturing executed with absolute zero-tolerance precision. This exploded view shows the complexity of reactor components. Manufacturing these systems requires specialized firms like MTAR Technologies, Walchennagar Industries, and WPIL Limited. Stage 2 shifts the economic opportunity from raw concrete to high-margin precision engineering. Stage 3 is the final objective: thorium-based reactors designed to leverage India's massive domestic thorium reserves. The primary technical hurdle is that thorium-232 is not directly fissile. It cannot be used as fuel in its raw form. This sequential graphic shows the solution. Inside the Stage 3 reactor, thorium absorbs a neutron provided by Stage 2, converting it into uranium-233, which is a highly efficient fuel for power generation. Operating these reactors requires specialized metals and alloys capable of withstanding extreme internal temperatures and intense long-term radiation. These novel materials require specialized manufacturing from Mishra Dhatu Nigam, from Bharat Forge, and Godrej and Boyce. Stage 3 provides the terminal point of the program: total energy independence achieved through a permanent, captive market for India's advanced metallurgy proxy stocks. This sprawling system map connects all three stages into one massive, functioning industrial ecosystem. The final layer of this ecosystem rests with the generation and utility companies like NTPC Limited and Tata Power, which will operate this grid and distribute the baseload power. This interconnected loop is the only way India can meet its 2032 industrial and decarbonization targets using its own natural resources. This infrastructure build-out represents a multi-decade capital expenditure cycle, creating sustained structural demand for India's heavy engineering and construction sectors. Stage 1 builds the base. Stage 2 multiplies the fuel. Stage 3 enables the thorium cycle. Understanding the engineering supply chain is only the first step in identifying the potential of this sector. To evaluate these proxy companies, we have to analyze their specific order books and financials. Subscribe and join us for Part 2, where we analyze the portfolio positioning for these listed proxies.